Okay, so this is a continuation of section 6.3. And our next objective is we need to find the highest exponent of a given prime P in factorial. This is equivalent to saying that we need to find the exponent such that P to the E divides in factorial, but P to the E plus 1 does not divide in factorial. All right? So we're going to state a theorem which gives us actually a formula for this highest exponent. But before we state that formula, let's look at actually an example and actually show how the proof would go. All right? This one. All right. Here is the example. Let's take n to be equal to 10. Then we have 10 factorial. This is going to be equal 1 times 2 times 3, 4, 5, 6, 7, 8, 9, 10. All right. Now, from here, we need to find, the 3, which appears on which one of these factors. All right. 4, 5, 6, we can write this as 2 times 3, then 7, then 8 is 2 to the third, 9 is 3 squared, and of course 10 is 2 times 5. And all together, we have also the 4, we could write this as 2 squared. So all together, we write this as 2 to the we have 2, and we have another 2, and the 3. Altogether, we have 8 of them. And then we have a 3 to the 4th. Then we have 3 to the 4th, 5 squared, and 7. So in other words, the E in this case, of course, is equal to 4. So this is the highest exponent of highest exponent of the P equation. All right. All right. Now let's see how we can actually derive this without displaying the actually the n factorial and find it by just counting how many 3's are there. First, we're going to look among the integers. Remember, we have this thing among the integers. 1, 2, 3, up to 10. There are 10 divided by 3 are divisible by 3. Or we could say this one among these integer or multiples of a 3. And these are, of course, 1 times 3, 2 times 3, and 3 times 3. All right. So these are the among these that are multiples of a 3 or divisible by 3. Then so there are these many of them. All right. And which one? And this number, of course, is equal to 3 and divided by 3. And this is equal to 3. And when you look at the last, which we have the first 3, and then the 6th has a 3 in it, and then we have the 9, it has also a 3. So these are the numbers coming from 3. Then we want to look at among these, again, among these integers, 1, 2, up to 10, that are multiple, or they actually are divisible by 3 squared. Okay, divisible by 3 squared or multiple of 3 squared are divisible by 3 squared. And these are the number of these is going to be 10 over 3 squared, or which is 10 over 9, and this is equal 1. Then we're going to look at among these which are divisible by 3 to the 3rd. Okay? So among 1, 2, up to n, divisible by 3 to the 3rd. And this one is going to be 0. It's going to be 10 over 3 to the 3rd. And this is equal to 0. Now, when we have the product, which is the n factorial, we're just going to add these up. All right? So this is the way we actually did count in the example. So together, all together, so the highest exponent of the 3 in n factorial is obtained by adding these, all the numbers that are actually divisible by 3 or divisible by 9, which is 3 squared, or divisible by 3 to the 3rd. Usually we can continue in here, but till we get to 0, and this is what we get. So we have 3 for the first one, plus 1, and this is equal to 1. All right. So now I hope the theorem that I'm going to state is not going to be a surprise, because that's exactly what this is saying. So this is Theorem 6.9. Says that if n is a positive integer, and p is a prime, actually p could be even bigger than n. In this case, the highest exponent is going to be 0. Means that there is no restriction on p in the formula that we have. Okay, so this is a prime. Then the exponent of the highest power of p that divide n factorial is this, equal to summation k equal 1 to infinity, bracket, n is the greatest integer function, p to the k, and that's it. Now, let me explain this summation. This looks like it's an infinite, okay? In fact, or note that the sum above is a finite sum, since n over p to the k equal to 0 if actually n becomes, if p to the k becomes bigger than n. All right? So if it's bigger than n, this is equivalent to saying that n over p to the k is less than 1, and this is equivalent to saying that this is going to equal to 0. In other words, after some point, all right, in this summation, the power of this prime p is going to be becoming bigger than n, and we are just hitting zeros. So this is, in fact, a finite sum. All right, and the proof actually pretty much follow the same as in the example. So what we're going to do, we're going to look at the integers from 1 to n and count the number of multiples of p till we reach n. Okay, here's the proof. And you're going to consider the integers. 1, 2, 3, up to n. And we're going to look at among these, integers, among these integers that are divisible, by p are, of course, if p is bigger than n, then we don't have any. Okay, so we're assuming that p is less than or equal to n. All right, among these integers that are divisible by b are p, 2p, 3p, and so on. And so the last one is tp, where tp is the largest integer, where p is the largest integer less than or equal to an integer such that tp is less than or equal to n. And or this means that t is going to be less than or equal n over p, and the largest integer in this case, therefore t is going to be n over p. All right. Then we're going to look again the integers that are among the integers 1, 2, up to n that are divisible by p squared are these: p squared, 2p squared, and the last one is actually, again, n over p squared times n. The same argument, we could use a t and so on. All right, and then we're going to look at the integers among these that are divisible by p to the third. And then we continue this process, and then the highest exponent we obtain by adding all of this. Okay, so we continue this process. And after the finite number of repetition, we obtain actually what we call the number of times p divides and this number is expressed, as I said, we have it as an infinite sum, but this is in fact a finite sum. Simply, this way we don't have to restrict ourselves to a finite number in here, n over p to the k and a bracket. Let's look at an example just using this formula. Let's find the highest power of a 3 in 1000 factorial, for example. So it's very hard to do this one by counting, okay? So here's an example. Let's find the highest exponent of 3 and 1000 factorial. So the e here is going to be 1000 divided by 3 plus 1000 divided by 3 squared. And we just keep doing this till we come up with this fraction actually less than 1. All right. And this, it turns out to be the highest exponent. It's going to be this, 3 to the 6, and the next one to it, and from there on, all equal to 0. Okay, so this is actually equal to 0, and it will be from there on. So you calculate this, and it turns out this is the 333 of those integers in the 1000 factorial contains a 3, all right? And then among those, they contain 9s are 111, okay? And that one contains 27, and so on. It's 37, and 12, and 4, then 1, altogether give us 498. So in other words, in 1000 factorial, 3 appears with the exponent 498. That's a very huge number. All right, of course, with the other of the 2 and the 5 and so on. And the other primes that are bigger, then the 1000 factorial all appears with exponent 0. Okay, so this is the highest exponent. All right, we have an obvious corollary to this, which says that we can write n factorial, the prime factorization of it. It's like this. So this is a corollary, and due to Legendre, okay. And so we refer to this as Legendre formula, which tells us that n factorial, then it is equal the product of primes less than or equal to n, and then we have p and summation k equal 1 to infinity n over p to the k. The same p, of course, which appears in all of these is the same p. This is not a different p. All right? So just basically what this formula is saying is in the n factorial, you collect all the primes, all right, and collect them into all together into one prime to the highest exponent in the product, then another prime, and so on. So this is the multiplication is over all the primes less than or equal to n. All right, let's look at other related type examples. Suppose I want to find the numbers between 200 and 500 that are multiple of 7. Okay, so we need to find how many. Example, find the number of integers that are multiple of 7 among the integers from 200 to 500. Well, so first we need to find the, we know how to find the, among the numbers from 1 to, among the numbers 1 to up to 500 that are multiples of 7 or divisible by 7. There are 500 over 7. So these are how many of those? And this one is equal to 71. And then we're going to look at among the numbers 1 to up to 199. Because we're going to include, this one is inclusive, okay? The 200 to and then 500. Of course, we don't have the 200, it's not multiple of 7, but in case we have some other number. Okay, so among these numbers that are multiple of 7 is 199 divided by 7. And altogether, this gives me 28 numbers. So then the numbers that are between them, okay? So the multiples of 7 from 200 to 500 is 71 minus 28. And altogether, this gives me 43 integers that are going to be multiple of 7 between these. And some of them, of course, multiple of 49, but at least they are also multiples of 7. All right, let's look at one other type of questions. We could actually use this theorem. Actually, this one we used earlier, the properties of greatest integer function in here. This theorem is not used in strictly, at least, for answering this question. Suppose we need to find the number of zeros. Example, let's find the number of zeros in 50 factorial. And this is in the decimal representation, of course, of 50 factorial. Actually, this question is equivalent to finding the number of tens in 50 factorial. So this is equivalent to find the number of tens in 50 factorial. So if I find, the number of tens, when we multiply, these will be 10 to a certain power. The highest exponent of 10 that appears is going to give me how many zeros actually in the product. All others, it's going to be followed by 10 to a certain power. And to do this, we're going to take the 2 primes that make up the 10. Okay, so this is equivalent to find the highest exponent of 2 and 5 in 50 factorial. And for the exponent of 2, let me call it E2. And this is going to equal to 50 divided by 2, 50 divided by 2 squared, until we get to, actually this one to 2 to the 5th. All right? 52 to the 5th, which is 32, and then 52 to the 6th. This is equal to 0, it will be 0 from there on. So when you do this calculation, you find this one is equal to 47. And in the highest exponent of 5, E5, 50 over 5 plus 50 over 5 squared. And this is it. That will be giving you actually only 2 of these, and this gives you 12. Now, to end up with powers of 10, we need to take the actually the minimum of these. So in other words, the number of tens in 50 factorial is, or in other words, the highest exponent of 10 is going to be 10 to the 12. All right? So this means that This implies that 10 to the 12 is going to divide 50 factorial, but 10 to the 13 does not divide 50 factorial, and which implies that there will be 12 zeros. So this implies 50 factorial has 12 zeros. All right. At the end, in other words, these are going to be at the far right end. All right. Here is one of the applications of the theorem to show that the binomial coefficient is in fact an integer. It's a fact that we use all the time, that we didn't show. In fact, it is an integer. Just take it by faith. And this is theorem 610. If n and r are positive integers, such that you could take 0 less than or equal r less than or equal to n, right? Then the binomial coefficient and r is an integer. All right. Now remember that n r is equal n factorial r factorial n minus r factorial. Okay, so we're going to show that actually this fraction looking number is in fact is an integer. So this is positive. All right, the idea here is again to take a prime factor of the denominator, find what's the highest exponent of it. All right, so you're going to find the highest exponent of any prime factor of the denominator. And then compare that with that of the numerator. Of course, if the highest prime exponent of the denominator or the numerator is greater than or equal that of the denominator, then of course this is for every prime factor, then this is going to be an integer. Means they would cancel out and we end up with actually an integer at the end. All right, so this is the idea. And this is where we're going to be using the previous theorem. All right, so we're going to let P, this we're going to take on one prime, and of course this is true for every prime. All right, so here's the proof. Let P be a prime factor denominator. Which is n factorial, which is r factorial times n minus r factorial. All right. And this comes from the r factorial. All right. So we're going to find individually the highest exponent of p in r factorial is this sum. K equal 1. I'm going to put to infinity, again, it's convenient. And this is r p to the k. And similarly, the highest exponent of p in n minus r factorial is also this. 1 to infinity n minus r over p to the k. Okay, so this sum runs maybe through different values. In other words, this becomes finite after so many steps, which is different than this. But we could use the same, index k. All right. Now let's look at this identity. So we have r plus n minus r. We know this is equal to n. All right. And then we can divide by p to the k. And then we're going to take the brackets of this expression. So we're going to take the bracket of this and the bracket of this. Now the bracket of this sum here, we put the sum actually in the middle here. So one of the properties of the greatest integer function, it says that the following is true. So we have the n over p to the k, which is equal, again, r over p to the k plus n minus r p to the k. And this one is bigger than or equal to, separate these into two brackets, this one and this one. Again, this follows by properties of the greatest integer function. Okay, x plus y, remember? So we have this. All right. Now, when we do the sum of these, k equal 1 to infinity, and all of them, 1 to infinity, and then we can have this 1 to infinity, 1 to infinity. So let me write the result nicely here. So we have the highest exponent, all right, of this prime factor of the numerator, of the denominator that we started with. It satisfies this property, k equal 1 to infinity, r e to the k, plus k equal 1 infinity n minus r over e to the k. So what this statement, what this actually inequality is saying, it's saying that the highest exponent of p, so this one is, this is the highest exponent of p in n factorial. And this is the numerator. That is in the numerator. All right, numerator of the binomial coefficient, of course. And this is the highest exponent of p in the denominator. Okay, is the highest exponent of b in the product, which is r factorial times n minus r factorial, that is the denominator. Yeah, this one is saying that, the numerator highest exponent is larger than or equal that of the denominator. So together, this implies that the highest exponent, when we cancel out, then we end up actually with an integer. Let me see how we're going to say this one. So in other words, p appears in the numerator at least as many times as it appears in the denominator, as it appears in the denominator. And of course, this is true for every prime, all right? And this, the net result is we get then all of this implies then the n factorial over r factorial n minus r factorial is an integer. So every prime in here appears as many, at least as many as in the denominator. So when you cancel all the primes, then we end up with an integer. All right, a quick corollary to this. If we take the product of r consecutive integers, regardless what they are, then this is divisible by r factorial. Let me write this corollary here. For a positive integer r, the product of r consecutive positive integers is divisible by r factor. All right, here's the proof. Let's assume that the largest, let n be the largest integer in the product of the R positive integer, the R consecutive positive integer. This implies the product is going to be equal, this is listed in a decreasing order. So it is, the largest is n, in n minus 1, n minus 2. The last one is going to be n minus r plus 1. So altogether there are r, and they are all positive. Okay, so all these are positive integers. All right, now it's not very hard to check that this product can be written as n factorial over r factorial times n minus r factorial multiplied by r factorial. Now, from the theorem, we have the n factorial over r factorial, n minus r factorial is an integer, k. Let me call it k, r factorial. All right? So where k is that product or that binomial coefficient. All right? So where k is equal n factorial r factorial r factorial or n r. This one is an integer, so the positive by the theorem. All right, so therefore we have n minus 1 of n minus r plus 1 is equal k r factorial, and this is exactly means that r factorial divides this product. And we're done. All right. The last thing I want to look at is how to use this greatest integer function to apply to some number theoretic functions. And here is the theorem that we're going to prove. Theorem 611. And let little f and capital F be number theoretic functions. Such that capital F of n d divides n of little f of d. Then, for any positive integer capital N, if I want to add up the values of capital F from little n equal 1 to capital N, f of n, then this is given by this formula. K equal 1 to capital N of f of k, then the bracket capital N over k. All right. before we prove this, actually, let me write the idea. Okay, so here's the proof, and then I want to look at an example through the proof. Okay, proof, and then we do the formal proof. All right. When we look at actually the left-hand side, okay, left-hand side, which is equal n equal 1 to capital N, f of n, and replace f of n by what it is equal to, which means summation d divides n of f of d. Then in this double summation in here, we're going to take n equal to 1 and run it through the the internal or the inside summation for n equal 1, and then we're going to take n equal to 2 and so on. So the idea is we're going to see that we're going to collect, all right, all the terms that equal with equal values that comes from f of d. All right. So let me write this down, and then we can look at an example. How we're going to achieve this. Okay. So this is the strategy that we're going to follow. Okay. Here's the idea. The idea of the proof is to collect terms with equal values of f of d, all right, in the double sum. In the right-hand side, which is this. Okay, the right-hand side of this. All right, let's look at actually at an example how this is done and how we could achieve this, and then the formula will follow immediately. So let's take n equals 6. Okay. So before we proceed to the formal proof, let's look at an example. That n equals 6. So we want to look at n equal 1 to 6 of summation d divides n of f of d. All right? So this is equal. First, we start with n equal 1. We only have one divisor, d of 1, which is f of 1. Then, we're going to take the outside n is equal to 2. We have two divisors. Let me put these between, braces in here. Then n equal to 2, we're going to have f of 1 plus f of 2. Then when n equals 3, again we have two divisors, f of 1 plus f of 3. Then the 4, we have f of 1, f of 2 plus f of 3, f of 4. Then 5, two divisors, 1 and 5. Then 6, we have f of 1 plus f of 2 over 3 and 6. Now we're going to collect, as we say, we're going to collect all the terms, all right, with equal values of f of d. All right, so the f of 1, how many of these we have? We have all of these, and there are 6 of them, okay? So let's do that. So we're going to say this is equal. Of course, it's equal. So this summation, n equal 1 to 6, d divides n, f of d is equal f of 1 plus f of 1 plus f of 1 plus f of 1. How many so far we have? 1, 2, 3, 4, 5, and 6. Now let's look at f of 2. F of 2, we have 1, 2, and 3. So there are 3 of those. And I'm separating these. We're going to put each one on each line. Then f over 3, there are 2 of them. There is this f over 3 in here, and f over 3 comes from the 6. All right, so we have 2 f over 3s. F of 4, we only have 1, f of 5, 1, and f of 6, 1. So each one of these have 1, 1, 1. So we have f of 4, f of 5, and f of 6. Also, this number of f of 1, it happens to be actually equal 6 by 1. All right, the greatest integer of 6, 1. This one is 6, 2. There are 3. So this is 6. And this one, 6 to 3, which is 2. And this is 6, 4, which is equal 1. And 6, 5 equal 1, and 6, 6 also equal. So this is the way we count, all right? Now let's see this one actually in the general case. And look among the integers from 1 to 6, because that's what we are counting, we're adding, all right? So how many of these are basically multiple of 1, multiple of 2, all the divisors of n, all right? So now, in general, for any integer k bigger than or equal 1, less than or equal to n, all right, all possible values of these that we're going to sum over, all right, the number of integers among 1, 2, up to n, which are divisible by k, divisible by k is given by n over k. That's what we did before, all right? And of course, these are coming from k to k and so on. All right, namely k to k up to n over k. So in other words, for each of these k's, f of k is a term of the sum B divides n f of d for n over k different values. So in other words, we have each f of k is basically repeated. Let me see if this is what we are saying. The f of k is a term of the sum for n over k different values or different positive integers if integer less than or equal to it. Now we put this together, which means that this implies that therefore we have the n equal 1 to n d divides n f of d would be the same as adding d equal 1 to n f of k and n of and remember that this one is also, this is equal n equal 1 to capital N of f of x. All right, couple of applications of this actually formula to the number of divisors, tau, and sigma, the sum of divisors. So this is as a corollary, and this would be that. All right, so here's a corollary 1. And a positive integer. Then the sum of n equal 1 to capital N. Now, n is the same as n equal 1 to capital N. And the proof of this is very, very straightforward. Remember that tau of n is equal to this. In other words, the function in here which we are using is 1 for every n. So when we apply the theorem, then we are saying this is n equal 1 to capital N of 1, okay, which is f of k times, let me actually write it as f of k or f of, let me see in here, actually f of n, then n by n. But f of n is equal to 1, so this is equal to n equal 1 to capital N of n by n. Let's look at an example of this. In other words, just to verify, actually, this is true by doing the counting, the summation using the values of tau, and then comparing it with what this formula is stating that sum should equal. Okay, so here's an example. Again, let's assume n equals 6. And let's count, look at the summation, n equal 1 to 6 of tau n. So we're going to do this one by calculating each tau to up to 6. Number of divisors, remember this one, 4, 5, and 6. So number of divisors of 1 is 1. Number of divisors of 2, 1 and 2. 3 is 2. 4, 1, 2 and 4, that's a 3. 5 is 2. 6, 1, 2, 3, 4, and 6, that's 5. Actually 4, sorry. 1, 2, 3, and 6. There are 4, right? So altogether, this gives me 40. Now let's look at the summation n equal 1 to 6 of n over n. So this is, which is 6 over n. So this is 6 over 1 plus 6 over 2. 6 over 3, 6 over 4, plus 6 over 5, plus 6 over 1. And this gives me 6, gives me 3, gives me 2. This one is a 3/2 1. This is 1. And no, I don't think I have 6 over 6. Sorry, 6 over 6 in here. And this is another one. So altogether, I hope we're going to come up with, let's see in here, 4, 10, 40. All right, so this verifies the statement. We have also a similar formula to the sum of divisors. Okay, so we have another corollary. Corollary 2. Again, we have n equal 1, capital N, sigma of n is equal to n over n. N equal 1 to capital N. The proof of this is again, remember that sigma of n is equal summation d divides n of f of n, f of d, sorry, where f of n is equal n. So now I want to do the summation on this. I do the summation n equal 1 to capital N. And instead of f of d, we take f of n, or f of k if you wish. You want to use the same notation, f of k. And then we have n over k. Let me change this is to k, maybe equal 1 to n and put it in here. All right, now f of k is we need a k. All right, so in other words, now this one is k equal 1 to n. F of k is just k and 4. All right, so this is the summation of the sum of the divisors. It can be calculated using just this regular sort of sum. okay, without talking about divisor. So this is the significance of these two formulas. All right, going to stop right here. We have one more section left in chapter 6. Hopefully I will have this recorded tomorrow.